So I will try to speak in English, and first of all, I want to thank the organizers of such a nice conference, and I'm very glad to be here and to meet so many friends and to celebrate the birthday of Andrei together with our other friends. I will talk about our joint result with Alexander Kolpakov and Alexander Mednych. And the title is clickbait, so it roughly outlines the main result of our work. The calculation of volumes in three-dimensional Euclidean, hyperbolic, and spherical spaces is a very old and difficult problem. The first result in this direction belongs to Tartaglia, who described in the form of a poem an algorithm how to calculate the height of Euclidean tetrahedron with some concrete given edge lengths. The formula which expresses the volume of Euclidean tetrahedron in terms of edge lengths was later given by Leonhard Euler while he worked here in Petersburg. And more precisely, let T be an Euclidean tetrahedron, then its volume is a root of some quadratic equation whose coefficients are integer polynomials in itself in terms of squares of edge lengths dij. So here, dij denotes the length, the distance, Euclidean distance between the vertices I and j. Surprisingly, but this result can be generalized for any Euclidean polyhedron. Ijad Hakovich Sabitov proved his celebrated theorem. So let P be an Euclidean polyhedron with triangular faces. Then its volume is a root of an even degree algebraic equation whose coefficients are itself integer polynomials in terms of lengths of edges of P depending on combinatorial type of P. So let's consider a simple example. We take a house P1 and the same house P2 but with broken roof. Of course, P1 and P2 are of the same combinatorial type, and we can require that the set of lengths of the edges are the same for P1 and P2. Moreover, we can assume that all the black edges here are of the length 1. Well, to be precise, we have to triangulate the faces, so we have to add diagonals to the walls and to the floor of this house. And we can assume that the length of diagonals is square root of 2. Then, due to Sabitov theorem, the volumes of P1 and P2 are just two different roots of some algebraic equation whose coefficients a1 dots an are integer polynomials in terms of edge lengths, but edge lengths are just units and square roots of 2, but we use the squares of the edge lengths, so a1 dots an indeed integers. Classical Cauchy theorem states that if a convex Euclidean polyhedron has rigid faces, then it is rigid itself. If we try to avoid this condition of convexivity, then it becomes not true. So there are known examples of non-convex Euclidean polyhedra with rigid faces. which are flexible indeed. So diagonal angles can be altering. The first known examples were given by Bricard very long ago, but so his examples were self-intersecting ones. The first true example of flexible Euclidean polyhedron was given by Robert Connolly in the late 70s. And shortly after that, Stefan presented a smaller example, which has only 9 vertices and 14 triangular faces. And it is shown, I mean, the Stefan's polyhedron is shown on this picture. So we need to pairwise identify the edges marked by same letters here. And it was believed until quite recently that Stefan's polyhedron is possible simplest possible, is the simplest possible flexible Euclidean polyhedron. But in last October, these 4 authors upload a preprint to archive with the following example. So they considered Euclidean pentagonal bipyramid with one triangulated face. So we displace one triangular face with 3 additional triangles and 1 additional vertex here. And they proved that actually this is a true flexible Euclidean polyhedron. So it has no self-intersections. Actually, this was checked by Viktor Alexandrov and yes, and Evgeny Pavlovich Volokitin, right? They checked that this family of polyhedra indeed has no self-intersection. An important consequence of Sabitov's theorem is a positive solution of a well-known Below's conjecture proposed by Robert Connolly and Dennis Sullivan in late 70s. It sounds that the generalized volume of a flexible polyhedron doesn't change when it is bending. And after Sabitov's theorem, it became an easy exercise to show that, well, the volume of a polyhedron under this flexing transformation cannot be nothing more but constant, since the set of all roots of a polynomial is a final set, but the volume should change continuously during the bending. A high dimensional version of Sabitov's theorem for Euclidean space of dimension greater than 3 was proved by Alexander Gayfulin. And here I should stop talking about flexible polyhedra and Below's conjecture, because this is a material for a separate big lecture, but I should go back to my subject. So let's consider a hyperbolic 3-dimensional space. It can be modeled in the upper half space model. So let me remind you roughly what it is. So H3 can be modeled in the upper half of the 3-dimensional real space. The third coordinate is positive if we endow it with metric S given by this expression. So the boundary of H3, which is called absolute, consists of all points at infinity. And the group of orientation preserving isometries of H3 is isomorphic to PSL to C. And an element G of this group which is 2 by 2 matrix with complex coefficients A, B, C, and D, acts on H3 by the following rule. So here, zeta is a complex variable, T is a positive real variable, zeta encodes 2 real variables, X and Y. And due to this definition of the metric, one can show that the geodesics looks like this. So geodesic lines are Euclidean semicircles and Euclidean half-straight lines orthogonal to the absolute, and geodesic planes are Euclidean semicircles and Euclidean half-planes orthogonal to the absolute as well. And it is easy to see why the group of orientation preserving isometries of H3 is indeed isomorphic to PSL2C, because, well, any isometry is a composition of reflections with respect to geodesic planes. But geodesic planes are of the form as shown in this picture. So reflection with respect to geodesic plane is determined by reflection with respect to the corresponding circle on the plane of absolute, or straight Euclidean line on the plane of absolute. We can consider them as generalized circles of the complex plane, and that's it. So the group of reflections with respect to generalized circles is generated by is nothing more but a group of fractional linear mappings with normalization condition. We can choose the normalization condition in this way, and it is known that that is a PSL2C. Some notations. We will refer a node K as a smooth, simple, closed curve embedded in a three-dimensional sphere, or more generally in some closed orientable three-manifold M. The node exterior is a compact three-manifold X, which is M without tubular neighborhood eta of K. And the group, the fundamental group of X, is called the node group, for the sense of simplicity, associated to the node. We recall that the boundary of X is a torus T, two-dimensional knotted torus T, and there are two simple closed curves on T, shown yellow and green in this picture. So we can call them a longitude and meridian, which intersect transversely in one point. These two curves generate the fundamental group of this two-dimensional torus, which is free cyclic group, direct product of the free cyclic group zeta by itself, which is usually referred as the peripheral subgroup. In the 60s, Walshausen showed that the data consistent in the node group plus peripheral subgroup is a complete not invariant. But the difficulty is that also powerful invariant, it is extremely difficult to work with. Usually we admit some loss of information to construct a usable but non-complete invariant. From the other hand, a classical way to study groups is to consider their linear representations. So after Walshausen results, one can study representation of node groups and should also try to keep track of some of the peripheral data. It's possible. In the beginning of 70s, Robert Riley at the University of Southampton worked on representations of the node groups in PSL2C, which is a group of rotation preserving isometers of H3, as you remember. After some time, he got a faithful representation of the figure 8 node group, which was a discrete subgroup of PSL2C. So, roughly speaking, one can say that Riley discovered the presence of the hyperbolic structure on the figure 8 node complement. And actually, this was a very first example of the hyperbolic structure on the node complement. After that, Riley showed that the same idea works for several other nodes and links, so-called excellent nodes, which were described later in his paper in 1982. Later in the spring of 1977, William Thurston announced an existence theorem of Riemannian metric of constant negative curvature on three manifolds. In particular, it turned out that the node complement of any simple node except in torical and satellite ones admits a complete hyperbolic structure. And in his work, he wrote that he was motivated by Riley's beautiful examples because before he visited Riley in Southampton. And in the previous talk, Zhenya Fominich already showed that also William Thurston constructed a figure 8 node complement in three-dimensional sphere by gluing together the faces of two regular ideal tetrahedra. So, in this sense, Thurston rediscovered the hyperbolic structure on the figure 8 node from the geometrical point of view, while Riley did the same from algebraic point of view before. The A polynomial of a node was introduced in already classical paper by Darrell Cooper and co-authors in Invenciones in 1994. It encodes not only topology of a node, but also geometry of its complement. The other concept that we deal with in our work is so-called degeneration and regeneration of cone manifold structures. It has been studied in many works, and in this regard, we refer to the results by Boileau, Lip, and Parti. So here is the definition of the cone manifold. So three-dimensional cone manifold is a manifold MK, which can be triangulated so that the link of each simplex is piecewise linear homeomorphic to the standard sphere. And MK is equipped with a complete path metric such that the restriction of the metric to any simplex in this triangulation is isometric to geodesic tetrahedron of constant curvature. So here is a formal definition, and let's try this very simple two-dimensional construction. So we consider a sector on the Euclidean plane with angle alpha. Then we glue the sides of this sector to each other. As a result, we get a two-dimensional cone, and we see that any point on this cone except the vertex has a neighborhood isometric to Euclidean disk. But this is not so for the vertex. So if we consider, for example, a circle centered at the vertex of a cone with some sufficiently small radius epsilon, then the length of this red circle will be epsilon multiplied by alpha instead of 2 pi epsilon for the usual Euclidean circle. This explains why the vertex is a singular point. The same construction can be done in dimension 3 and in any dimension. So consider a wedge in three-dimensional sphere with the angle alpha, diagonal angle alpha along the edge of this wedge. Then we pairwise identify the faces of this wedge. Then we get a local structure of a cone manifold, three-dimensional cone manifold. And the image of the edge of the wedge is a singular set with a cone angle equal to diagonal angle alpha along it. So let K be a knot embedded in three-dimensional sphere, or more general, in some close to orientable three-manifold M. Let's denote C alpha, the corresponding cone manifold with underlying space M, and cone angle alpha along the singular geodesic K. We shall assume that K is a hyperbolic knot. That means that the complement of the knot in M has a complete hyperbolic metric of finite volume. And also we assume that the hyperbolic structure on the cone manifold C alpha exists for cone angles alpha from alpha 0 minus epsilon to alpha 0 and degenerates into Euclidean structure when alpha attends to alpha 0. And vice versa. We can consider an Euclidean manifold C alpha 0. So alpha 0 is the value of a cone angle responsible for the presence of Euclidean structure on this cone manifold. So we take now an Euclidean cone manifold C alpha 0, then a hyperbolic or spherical cone manifold structure can often be regenerated. Namely, it will be hyperbolic for alpha to the left side from alpha 0 and spherical to the right side from alpha 0. And this fact was shown in the paper by John Partee in 1998. And actually, the conditions are sufficiently weak. Since C alpha, the hyperbolic cone manifold structure, converges in the Gromov-Hausdorff metric after an appropriate rescaling to Euclidean cone manifold C alpha 0, then one can define the associated normalized Euclidean volume. Well, why we need it? In Euclidean geometry, there is a phenomenon of similitude. But there is no similitude in hyperbolic or spherical geometries. So due to similitude, we need to change the unit of measurement in Euclidean space. Or in other words, we should normalize Euclidean volume somehow. So here in this definition, we use the length of the closed singular geodesic L as a unit of measurement, unit of length. So here is a more or less standard definition for the normalized Euclidean volume. So this is the notation, and here is the definition. So this is the limit while when alpha, cone angle alpha tends to alpha 0, the value which is responsible for the presence of Euclidean structure, tends to alpha 0 from the left-hand side, so from the domain of existence of the hyperbolic cone manifold structure. We take the hyperbolic volume of cone manifold C alpha and divide it by the length of the singular geodesics, the length of the knot, to the power of 3. Yes, so this slide is just to say that the hyperbolic volume of cone manifold is an important quantity. Let me skip it. And this slide is just to say that the normalized Euclidean volume of the cone manifold is important over a hyperbolic knot is important quantity itself. Let me skip it as well. So the number theoretic nature of hyperbolic volumes is usually highly intricate. For example, in the previous talk by Zhenya Fominih, we used the volume of regular ideal tetrahedron for many times. Well, this is a very well-known volume. There is an exact formula by Milner. One can compute it as a 3 multiplied by Lobachevsky function in pi over 3. Okay, everybody knows the exact formula. But still, this is an integral formula. We can compute it with we can compute it numerically with thousands of digits after the comma, but still nobody knows if this number is algebraic or not, or even if this number is rational or irrational. So the main result of our joint work with Alexander Kolpakov and Alexander Mednych is that the normalized Euclidean volume is an algebraic number. And in many cases, we give a method to compute its minimal polynomial. So there are two references here. So this work of Donzagier has a good explanation of the number theoretical nature of Euclidean of hyperbolic volumes and why it is very difficult. And here is our work. The proof of the main result contributes use a modified version of the classical A polynomial. So while the classical A polynomial uses, roughly speaking, the complex length of the singular geodesics, we use how to say real version of classical A polynomial, which contributes with the real length of the singular geodesic, and it appears very suitable for computational purposes. And let me define it. Okay. So we assume that the fundamental. Okay, we start with. Let me define what we call real version of A polynomial, and we suggest to call it Rayleigh polynomial. We start with the classical A polynomial, A in variables m and n. I will explain these variables in the next slide, I think. And then following to approach by Hilden, Lozana, and Montesinos. So actually, this approach was proposed independently by two groups of mathematicians, by Spanish mathematicians Hilden, Lozana, and Montesinos, and independently by German mathematicians Helling and Meinecke in the mid-90s. So following this approach, we choose the canonical longitude meridian pair in the fundamental group of the knot complement in such a way that we associate the matrices in SL2C of this form to the meridian and longitude. So here we have 2 by 2 complex matrices. Here is the exponent of I alpha sub 2. Alpha is cone angle, and here we can see exponent of gamma sub 2. Gamma here is equal to L plus I phi. So roughly speaking, it is a complex length of the singular geodesics singular closed geodesic or the knot K. So L is the real length of K, and phi is some angle. Well, as you remember, we consider a knot as a simple closed and smooth curve embedded in some three manifold. So we can associate local basis to each point of this knot, like Frenet basis, and then we go. It consists of tangent vector, normal vector, and p-normal vector, and we can go along this smooth closed curve, the knot K, once, and when we come back to the starting point, the normal vector is rotated to the angle phi. So this is angle phi. By the way, this is more or less general procedure how to find a linear representation of the knot group. And here the matrices here have geometrical meaning actually. So these are rotational matrices along the two skew edges, along two skew axes of rotations. And here in this picture, we show actually in some cases this approach allows us to construct a fundamental polyhedron for the knot complement, or more general for the cone manifold of the knot. And these two matrices are responsible for the rotation around these two skew edges of this fundamental polyhedron. So one edge is here, the second is above, is below, and well, so the diagonal, these two skew edges, after gluing the faces of this polyhedron, gives us the singular set, the singular geodesic. The diagonal angle along these two skew edges gives us cone angle of the resulting cone manifold. And actually the rule how to glue the faces of this polyhedron to each other can be given by identity in the group. An important property of a polynomial is that it is equal to 0 when the variables L and M are of this form. So L is exponent of gamma sub 2. Again, you remember this linear presentation. And M is exponent of I alpha sub 2. So we introduce the auxiliary polynomial A with a hat in such a way. Then to construct Rayleigh polynomial, we use the following procedure. So we consider first a resultant of two integer polynomials, with integer coefficients, the classical A polynomial and auxiliary polynomial A with the hat with these variables, and we consider the resultant with respect to one variable L. So we call it R1. Then we consider the next resultant of R1 and this simple polynomial. And we call Rayleigh polynomial as a factor of R2 that corresponds to the hyperbolic structure on the knot complement. Actually, R2 every time has two factors. One of the power 4, it arise due to some lifting, and the remaining part, the remaining fraction, we call it Rayleigh polynomial. And this Rayleigh polynomial has a good property. It is equal to 0 if and only if the variables here are of the form. The first variable is exponent of I alpha sub 2, and the second is just the exponent of real length of the closed singular geodesic. And the main, to be precise, the main result can be formulated as follows. So let C alpha be a cone manifold with underlying space 3 manifold M, closed orientable 3 manifold M, and singular set a knot K with a cone angle alpha along it. Assume that the fundamental group of the knot complement has a Holomy representation in SL2C, and C alpha, cone manifold C alpha, admits a hyperbolic structure for cone angle alpha from alpha 0 minus epsilon to alpha 0, and degenerates into a Euclidean structure when alpha tends to alpha 0. Then the normalized Euclidean volume of C alpha 0 is always an algebraic number. Well, these two assumptions formulated in the second sentence of the theorem is not so, these two assumptions that the fundamental palindrome has a holonomy representation, fundamental group has a holonomy representation in SL2C, and C alpha admits a hyperbolic structure to the left-hand side from alpha 0 when alpha 0 is responsible for Euclidean structure. These two assumptions are sufficiently weak. This follows. This was shown by John Partee. So, of course, I have no time to explain the proof, but let me show one important step. So here is a very well-known classical Schläfli formula. It relates the volume differential of the hyperbolic cone manifold C alpha. So here is a constant depending on the dimension. Alpha is the length of the closed singular geodesic, the length of the knot, real length of the knot, and the differential of cone angle alpha. So let's recall the definition of the normalized Euclidean volume of cone manifold C alpha 0. It is written here again. So this is the limit. When hyperbolic cone manifold structure degenerates into Euclidean one, the hyperbolic cone manifold degenerates into a single point. So when alpha tends to alpha 0, the hyperbolic volume here tends to 0, and the length L in the denominator tends to 0 as well. So we have the uncertainty of the type 0 divided by 0 here. So we can try to use the L'Hopital rule. So we take derivatives of the denominator and denominator here. But the derivative of the hyperbolic volume with respect to cone angle by Schläfli formula is nothing more but minus 1/2 of L. And the derivative of the denominator, which is L to the power of 3, the derivative of the denominator can be rewritten as follows. So we have this guy. The limit of 1 divided by the derivative with respect to cone angle of the square, the length to the power of 2. And it is important because the asymptotic behavior of the length of the knot itself, while alpha tends to alpha 0, while hyperbolic structure degenerates to Euclidean one, the asymptotic behavior of the length L is bad. But the asymptotic behavior of the length to the power of 2 is good, and we can control this guy. And then step by step we use the technique of resultants to show that this quantity is a root of some polynomial with integer coefficients. And since the proof is constructive one, then we can provide an algorithm or pseudocode how to compute its minimal polynomial. So we use a classical A polynomial as a input data for this algorithm, and then we have 19 steps. For example, on the fourth step we introduce the auxiliary polynomial a hat, a with a hat. Then on the fifth step we take the resultant of the classical A polynomial and A with a hat in terms of variable L, one variable L. Then on the sixth step we take a resultant of R1 from the previous step, and this polynomial in terms of L conjugate, and so on. And on the last step we get the polynomial. And let me show just one example. I think I have 1 minute. So here is the knot 5, 2. The diagram is shown here. The A polynomial for this knot is embedded in three-dimensional sphere is known. Here it is. We use it as a input data for our algorithm. And by performing the algorithm, we obtain that a normalized Euclidean volume is of this form. Actually, the normalized Euclidean volume of the cone manifold over the knot 5, 2 was known. I mean, there was known an exact integral formula for it. And one can compute any number of digits numerically. But now we know that this quantity can be rewritten in radicals in such a way. And the minimal polynomial for this guy is written here. So thank you for your attention. Да. Да. Ну, единица, деленная на нее, и предел. Ну, вот мы берем результанты последовательно. Сначала от А полинома и, значит, вспомогательного полинома, овеществляем его. Ну, в результате получается полином несколько более высокой степени, но уже вещественно значный, с целыми коэффициентами. Вот, из него выделяем следующий результант. Ну и в итоге получаем многочлен, корнем которого, одним из корней которого является вот это число, да, единица делить на квадрат длины. ее предел при альфа, стремящемся к альфа нулевому. Это на самом деле получается у нас как бы мы показываем не что объем хорошая величина, а что единица делить. Да, единица делить на длину хорошая величина. Ну, то есть длина в квадрате это хорошая величина, а объем в пределе равен обратной к ней. Вот, поэтому, кстати, здесь вот старший коэффициент большой, а младший вот единица получился. Да, помимо вот этой, скажем так, теоретической теоремы существования, да, теоремы существования целочисленного полинома, корнем которого является нормированный Евклидов объем. И помимо вот этого алгоритма мы, конечно, много примеров просчитали. У нас есть вот просчеты для всех узлов с числом перекрестков 7 или меньше. Вот это довольно много. Да. Ну, почему именно двухмостовые мы считали, применяли этот алгоритм? Вот чтобы быть честным, да, именно так, потому что в качестве входных данных мы используем А-полином, а для двухмостовых, для бесконечных семейств, вот двухмостовые узлы как раз и известно, как его считать, да. Для зацеплений нет, это ограничение нашего, значит, метода. Для зацепления нужно сначала определиться с тем, что считать за единицу длины в евклидовом случае. То есть там же как бы получается несколько компонентов. Да, может быть, надо рассматривать какую-то вот для двухкомпонентных зацеплений нужно рассматривать уже двухпараметрическую вот алгебраическое многообразие какое-то. Да. Ну, главное соображение, что должна быть непрерывность при переходе от гиперболической структуры через Евклидову к сферической. На самом деле, такие примеры, ну, для конкретных зацеплений, сам же Партий рассматривал. И у него получалось так, что для двухкомпонентных зацеплений, вот есть у нас один конический угол, другой конический угол, и вот есть какая-то кривая, ну, прямую нарисовал неудачно, какая-то есть кривая, которая отвечает, каждая точка на ней отвечает евклидовой структуре. Даже, может быть, удобнее не сами конические углы рассматривать, там их косинусы. И слева от нее находится область, в которой гиперболическая структура присутствует. Справа от нее находится область, в которой сферическая структура. Да, конечно, да. Вот, ну, и надо определять нормировку в евклидовом случае для нормированного евклидового объема так, чтобы объем менялся непрерывно при переходе через евклидову вот эту вот структуру в любом направлении, в любой точке. Да, получится уже, да. Когда не одна переменная, сложнее, потому что вы можете тогда из формулы Шлефля получить, ну, систему дифференциальных уравнений, да? А не одно. Да. Да, ну есть, да, Андрей Юрьевич точно говорит, что есть как так называемый главный параметр, с помощью которого можно запараметризовать это все. Должно получаться красиво.